Hello everybody, welcome back to another installment of the Damage Control Assistant Senior Enlisted Curriculum. I'm Lieutenant Timothy Mueller, and in this video, we're going to cover Chapter 7, Lesson 1, where we talk about writing ship and correcting for a list. Now, so far in these videos, we've talked about G2, that being the horizontal shift of the center of gravity, causing a list on a vessel. We've also looked at how to measure a list based off of statical curves of stability. Well, sometimes you don't need or you can't get that information from the statical curves, and you need to find out exactly what you're going to list to or how you're going to correct your list based off of equations and things that you know already about the ship without doing statical curves of stability. So we've seen previously in videos that a ship normally with G and B, or well with G on the center line of the ship, is going to be at an even keel. If we move that G over, we know it's going to start listing. Move G horizontally, B is going to swing through an arc until it establishes another equilibrium point. We know that this off-center G causes a list on the ship. However, on board, so if we're in Damage Control Central or on the bridge or somewhere else, we can't measure this G1 here. There's no instrument or any chart that's going to directly tell us our G is 2.5 feet off center line or anything like that. However, there are what's called inclinometers on the bridge in Damage Control Central and several different stations that's going to tell us in real time exactly how far the ship is listing or rolling at any given instant. We have to use our knowledge of the center of gravity. We have to use our knowledge of righting arms and inclining and righting moments, as well as what we can measure instantaneously from these inclinometers to somehow develop a plan in correcting a list, or if we're shifting or we're removing fuel from a fuel tank on one side but not the other, how far the ship is going to be listing after we complete that evolution. So now that we know that we can immediately measure a ship's inclination, we have to somehow translate horizontal shift of the center of gravity into inclination. Start working with that. Then we can get some sort of a characteristic of the ship, which is going to tell us how far or how much of a moment we impart on the ship to heel or list, basically incline the ship over so many degrees. So now let's take a look at a ship that's actually listing. So right now it is in an equilibrium point where the righting force of the ship, so the center of buoyancy, is completely counteracted by the movement of the center of gravity. So right here, we have a ship that was originally on the center, originally on even keel, and we took this W, this weight, and we moved it horizontally some distance D. That shift is going to cause a horizontal shift in center of gravity, as we already know, and it's going to impart an inclining moment onto the ship. The ship is going to act accordingly from that inclining moment until the righting moment brings it back. Or sorry, the inclining moment equals the righting moment. Once that occurs, then the ship will just stay there until something happens to the inclining moment or the righting moment to change that equilibrium. So we know that we take W and we shift it horizontally this distance D. When the ship actually inclines, however, this D is not going to be the moment that's actually imparted onto the ship. We know that the force of gravity goes straight down. So the actual force of gravity doesn't move D. It actually moves this perpendicular distance, which I'm going to call here X. So in this triangle, this point is where the weight started, this point is where the weight ended, and then this X is that perpendicular distance that the force of gravity actually shifted. That's what the actual inclining moment is going to be reacting to, not this lowercase d. It's going to be that X. So how do we solve for X? Well, we know D, or we can measure D, or we can find it out. We can have a plan. So X is going to be lowercase d times the cosine of theta. Theta is going to be our angle of inclination, like we've seen before. So with this, our inclining moment is going to be W, which is the weight that we've shifted, times just this x, which is d times cosine theta. Now let's take this and just put it off to the side a little bit. Now let's evaluate the writing moment. If we take the writing moment, we can draw another triangle, and this is one that we've seen way back in chapter 1 and chapter 2. We have GM, which is our metacentric height, the distance from G up to M, GZ being our writing arm, and theta being our angle of inclination. GZ, like we had talked about before when we were doing sign corrections, GZ equals GM times the sine of theta. Now that's the writing arm. If we want to get the writing moment, right here, we just multiply that by the displacement of the ship. So writing moment equals the displacement of the ship times GM times the sine of theta. At this point in equilibrium, the ship's inclining moment is the same as the writing moment. So if we set them equal to each other, so IM equals RM, so W times D times cosine theta equals displacement times metacentric height times sine of theta, and then start to manipulate that, all we have to do is divide both sides by cosine of theta, and then we'll get an expression that's going to tell us how much of a horizontal shift in some sort of a weight will give us or it'll actually tell us at what equilibrium point we'll have the ship finally settle out at. Commonly, in DK school, we're going to use 1 degree. We call it moment to heel 1 degree, or moment to list 1 degree. This MH1, which I'll refer to in all the future videos, equals delta times GM times tangent of 1 degree, which is just 0.01746. So if you take 0.01746, multiply it by the GM of the vessel, then multiply it by the displacement of the vessel, it is going to tell you how much of a moment has to be imparted onto the ship in order for it to list over or incline 1 degree. Now, when we here at DK School refer to MH 1 degree, it's only that moment to heel 1 degree. If we have to correct a list, or if we're doing more than just the MH1 moment, then we know that we're going to go more than just 1 degree, or we're going to have to impart more of just that moment to correct more than 1 degree. With the small angle approximation, we're talking about tangent, which is sine divided by cosine. We can use that small angle approximation to take sine theta equals just theta, like we've seen before with the radian line, and then cosine theta just equals 1. Now, if we do that approximation, then our sine theta, or our tangent theta, just basically becomes sine theta at very, very small angles, so 0 to 7, maybe even 0 to 10, which means that if we took 7 degrees here, say we wanted to correct 7 degrees, it's not very different from the answer you would get if you just took a tangent of 1 degree and multiply it by 7. And you can do that on your own. Just take any displacement, say 2,000 long tons, take any GM, just say 3 feet, and then do tangent of 1 degree, and then multiply it by 7. So you're hypothetically correcting a 7 degree list. And then do the same thing, same displacement, same GM, but do tangent of 7 degrees. You'll get a very slightly different answer. However, it'll be very similar to what you got when you just took tangent of 1 degree and multiplied it by 7. Now, if you've watched previous videos, I've mentioned that listing is caused by internal forces on the ship and heeling is caused by external forces. With all this weight shifting, it sounds like we're doing internal force changes of internal forces, which means that we would be listing. However, I talk about moment to heel 1 degree. And I only use heel just to get rid of some confusion that might happen with other acronyms in this class. When it comes to heeling or listing, no matter how the forces are acting on the ship, inclination is still just inclination. So it really can be resaid as moment to incline the ship 1 degree. But that would get confusing with like tons per inch immersion, which we had talked about. So we just try MH1 looks very different than anything that we've used in the past. So we have MH1, which we already know is displacement times metacentric height times, if we're talking about 1 degree, we can use 0.01746. So if that is the moment that we need in order to correct 1 degree of list. If we wanted to correct 5 degrees of list, we just multiply it by, which would be 5, or our list. And that's going to tell us how much of a moment we need to impart on the ship to correct or to incline some number of degrees. If we rework this, and our moment needed, we rewrite as W times D, W being some weight that we shift, D being that horizontal movement. The list equals W, the weight that we shift, D, the distance that we shifted, and then MH1, which is our moment to heel 1 degree. So now we have everything that we need in order to take some very simple characteristics about the ship, which we should be finding every day through our basic calculations, and then taking what we can measure immediately from an inclinometer, doing some very basic calculations, then we can use this to make a plan on how to correct that list. So now let's go into an example problem where we actually take these two and put them into action. All right, so now that we have our tools on correcting list and righting the ship, let's look at an example problem real quick. So with this vessel, we are listing 7.4 degrees to starboard. We have 2 ballast tanks, 4 TAC 110 TAC 1 and 110 TAC 2 TAC whiskey, and they are 50% full. Each one has a 100% capacity of 15,000 gallons, meaning that each tank has roughly 7,500 gallons in it. And the center of gravity of those tanks is 26 feet apart. 1 long ton of seawater equals 261.8 gallons of seawater. So if we want to move 1 long ton, we know that we have to move right about 260 gallons in order to get that same weight. Can we right the ship with what we've been given? Some basic characteristics of the ship at this moment. The KM, so the height of the metacenter, is 24 feet. KG, the height of the center of gravity, is 20 feet. And the displacement of the ship is 1,400 long tons. So step number 1, we have to find the moment to heel 1 degree. And that's just the displacement of the ship times the metacentric height times 0.01746. So we know the displacement, 1,400. We know the metacentric height, and that's going to be 4 because our Km is 24, Kg is 20. So we subtract them from each other and we get 4. Multiply by this number, and we're going to get 97.78 foot long tons per degree, which means for every roughly 98 foot long tons of moment that we shift weight, we're going to have the boat incline 1 degree. So now we have our MH1. Now we have to go to list. Our list is 7.4. That was given up here. This W, we don't know yet. This 26 is the distance that we're shifting. So we're going from 1 ballast tank on the starboard side. We're shifting over to the port side. It's going to be shifted 26 feet. And then we have 97.78, which was our MH1, moment to incline the ship 1 degree. Now, if we rework this and solve for W, W is going to be 27.83 long tons. Now, if you are looking at flow meters or actually trying to plan and see how much weight you have in one tank and how much space you have in another, this might not be a very useful number for you. You have to go in gallons. So we use this information that we had up here to convert our long tons to gallons. We know it's 261.8 gallons per long ton. So we're just going to convert to gallons by multiplying the 27.83 long tons by that conversion factor. And we're going to get 7,285.5 gallons. If our one tank has 7,500 gallons in it, and the other tank is at 50%, which means that it has room for another 7,500, that means we're not shifting the entire tank, and we're not filling up that entire, the other tank. So we can correct the list with just these tanks. Now, as you saw in this example, we shifted a weight a known distance. You can use this formula in order to shift a known weight an unknown distance, or an unknown weight an unknown distance. You just have to kind of give yourself boundary conditions on either the weight or the distance, solve for the other variable, and see if that's practical in your situation. You might see problems like this on board of a ship, where you have to shift several tanks at once, or you might even have to add water to one side. If you add water, you're going to have a weight addition, which is going to drop the center of gravity, which is going to change your kg. Yes, your GM. It's going to change your kg. Your km isn't going to change very much, so your GM is going to change, and your displacement's also going to change. How would you actually calculate that out? Well, that's going to be in our next video, where I talk about changing displacements and changing GM. We're going to go through an example problem, just like this, but we're going to change the size of the tanks. And we're going to see exactly how much more calculation there is in order to solve that. But that's for the next video. Until then, I'm Lieutenant Timothy Mueller, and I hope you have a great day.